It's great to see you all here. This is my first AWS Public Sector Summit, so this is a lot of fun. We were here yesterday, we're here today and tomorrow, and already having some really amazing conversations with customers and partners and looking for new ways to bring the cloud, in particular in my case, to the space, the aerospace, and the geospatial intelligence areas. So about 2 years ago, AWS looked across the spectrum and saw all the rapid growth in the space enterprise. And those of you here, I'm sure I don't have to tell you, but as you look at the total number of satellites that are being launched around the globe every year, which, by the way, we're told are going to, depending on the study, either triple or 10x increase over the next decade, right? So there's a big swath. But thousands and thousands of new satellites on orbit, new companies entering the market every day, more global spending on space than ever before, and moving to a $1 trillion industry. So AWS recognized all the value and benefit of the cloud in support of the space, aerospace, and geospatial industries. And so we stood up a dedicated team last year that I have the privilege of leading, the aerospace and satellite team, so that we can sit down and work with companies just like Descartes Labs and help them change the game and change the way we operate in space. When you look at all those satellites that are going to be launched over the next decade or so, we are literally going to have the problem of having more data than we know what to do with, right? We will be bringing down petabytes and petabytes of data. How do you make sense of that data? How do you draw insights from that data? How do you solve problems with that data? Enter my good friends at Descartes Labs. So the U.S. administration's budget for 2022 identifies the top 2 threats to the United States and its allies as China and climate change. And Descartes Labs is uniquely positioned to support both of those key missions, and Adam will talk to you about how. They've also demonstrated their supercomputer prowess. We teamed together, Descartes Labs and AWS, and we competed in the annual global Top 500 Supercomputer Challenge this past year. And I'm proud to report Descartes Lab, building on AWS, came in number 40 globally on the Top 500 Supercompute list, which shows how they're bringing high-performance computing to AI and ML to really extract data or insights from their data. So in just a moment, I'm going to introduce Adam Smith. He's co-founder and head of strategy. During his 20 years on Wall Street, Adam saw that traders are willing to spend billions of dollars for even a millisecond advantage over their peers in decision-making. And that's absolutely then what he realized and recognized the value of context-rich, timely data could do. So Adam joined forces with scientists from Los Alamos Labs, one of our foremost labs in the U.S., to create Descartes Labs. And you will love hearing from Adam, as I have, how they're simultaneously working to help save the planet, priority number 2 for the U.S. government, and protect America and its allies, priority number 1 for the U.S. government. And he's going to share a little bit more why they chose to amplify their impact on AWS. So my friend, Adam Smith, come on up.
Thanks, Clint. Appreciate it. Okay, thank you, Clint. And thanks to AWS for having us here at the summit to talk. We appreciate it. My name is Adam Smith, as Clint said, and I'm a co-founder here at Descartes Labs. So I'll introduce the company and then walk through some of the way that we see some of the challenges that Clint just outlined. Descartes Labs is a geospatial analytics company. We were born out of Los Alamos National Lab, and our purpose is to take sensor data of the Earth and turn it into meaningful information for our partner organizations, from government, from commercial enterprise. And we do that by harnessing the flood of hundreds of different inputs that come from terrestrial and space-based sensors. This represents hundreds of terabytes a day, potentially, and hundreds of petabytes in total, in an effort essentially to remap the Earth every day. And so with this flood of data coming in, we're able to build then some artificial intelligence technique that recognize the kinds of patterns as they emerge that predict outcomes that our partners most care about. As Clint said, topics that range from military activity in China, or production changes in a commodity supply chain, issues with sustainability. So we help the leaders of our partners make better decisions by recognizing the emergence of these patterns, and as they emerge, these patterns map to predictively those outcomes they're most interested in, and thereby create actionable intelligence for them. It's one thing to sort of report what has happened. It's another to be ahead of what is most consequential for these organizations. We've researched and deployed over 300 of the types of patterns that you see here. And generally, as I said, they fall into the buckets of national defense, sustainability, commodity supply chain, but they all leverage that same digital twin of the planet that we're creating by ingesting all of these sensor data sets. Now, one thing that makes us a little bit different from our peers is our approach. Historically, geospatial intelligence largely, I think we see as a secondary source of intelligence, meaning someone or something had a question about a location, and then geospatial data is quite useful to zoom in and confirm or modify that thesis, but inherently it's supportive technology. It's not generative of the thesis. If you look at commercial satellite, the commercial satellite industry, for instance, it's quite adept at tasking an image and delivering it to that location, but it has to be told where to look. And so at Descartes Labs, we're trying to take this different approach that addresses the set of questions where you don't know where to look ahead of time. We think the most consequential patterns are surprises. By definition, you don't know where they're going to occur before they occur. And so our solution to that is to ingest all of the data all the time and search using ML for those patterns that matter. And this inversion of approach is really, I think, a way that we try to promote GeoINT to be more of a primary source of information. And so we use our product called Global Change Discovery, and I'm now going to show you a bunch of examples from the different realms that I mentioned on how that works. So I'll start with a stylized example because we sanitized this a little bit, and we're going to look at copper smelters. But we're not just interested in copper smelters in terms of like the location of each of the facilities. We'd like to know the subset of all of those factories that have low inventory and were recently turned on. And that pattern puts us into a more meaningful form of intelligence than just the object detection approach of saying those locations. It's what's the pattern of life that represents that activity. The first step is to use computer vision on a map to find those locations. That's relatively straightforward, even off the shelf these days. And we do that, but then we're going to add two vectors of improvement. The first is that we're going to search across a number of layers, not just the visual spectrum, and that we're going to do it globally and continuously, not just within an area of interest. So before we start, again, why do we care about this? And as I said, there's really three general customer sets or partner sets that do look and value this approach across business, sustainability, and defense. So if you look at a business analyst, the reason they might care about a factory that's recently turned on rather than just its location might be if they're selling raw material. Knowing which factory has low inventory and is just turned on is a sales target. If you're in the financial community, the additional supply into a commodity market is often negative for prices, so you might sell your futures contract. In sustainability, a downstream analyst or leader for, say, a construction company who's purchasing from the copper smelter now has the ability to accurately dimension the amount of carbon emissions coming from their total supply chain. Scope 3 emissions is going to be a requirement in the future. For military leaders, they now have the ability to look at the economic backdrop of a near peer, have it quantifiable and persistently tractable. So let's look at this example and see how we get this information to these folks. So we'll start in China in our example, and we have a known location in Jingguan. We can outline the factory and then give that to our system as training data. The system can then find all the matches. We found 37 in our example. And we can then click on any one example and bring up the image. Okay, so that's our baseline. So now with those known locations, we turn to adding resolution to this pattern that we're searching for. And the first one is inventory, and for that, we're going to turn to a radar data set. Specifically, in this case, the Sentinel-1 synthetic aperture radar from the European Space Agency that's able to see outdoor stockpiles. At Descartes, as I said, we're ingesting all of this data, and we're lining it up against all of the other data. So knowing the location of the factory, we can just look at the corresponding position in the radar and very quickly see there is inventory in the white pixels here. So we'd exclude this one from our population. Now let's look to see if it was recently turned on. For that, we're going to use a thermal data set. Again, we've ingested the global fire hose of this data, the full archive, and co-registered it with all the other data. So here we can see this location is on by the white spot of heat there. But if we add a temporal slice to it and say, look a month ago, we can see that in fact it was off. And so that pattern of off to on within a month now becomes a persistent search term in the pattern that we're going to be looking for going forward. We can add additional data sets. This is cell phone location, and we can see those pings mean that there is staff at the factory right now, but that a month ago there were fewer. And so now we're down to 7 targets. And that ability to search a fused set of data layers using our system adds a richness to the search that is a very powerful technique. It moves from object detection to pattern of life. It moves from responsive to predictive. Okay, so now that we've got our signature set, we can define an area of interest. Those 4 sites we can then time series. The system allows an analyst to set a parameter or threshold so that if, say, they'd like to be alerted that the number of people entering that facility is a standard deviation different from the trailing average, the system will send that alert. And now that runs in the background, the signature, the parameters, it gets included into this list of saved patterns that we're searching for and is just passively constantly going so that as we're taking in the latest information, if there's a new match, it will alert the analyst. That moves the system into something that is supportive and generative of an idea that's important. The other piece of this, the other vector of improvement, is the change discovery. So if there's a new pattern that occurs outside of the area of interest, the system can let us know. And so this ability to look at complex patterns, to threshold values, to discover new change is really a powerful system that our analysts across these 3 domains have used consistently. Now I'd like to give an example, a real-world example of this idea of change discovery. This is the idea that you know what you're looking for, but not where to look for it. And a few months ago, there was a research group that uncovered some activity in the Gobi Desert. There was a missile silo that was being built by the Chinese. It was publicly reported. And we took that location and looked at the signature, the pattern that was forming. This is a radar layer of that pattern. And we gave it to our system to search for matches. Within an hour, we had found a potential second site a few hundred miles away. This was accomplished by searching thousands of square kilometers of newly acquired imagery almost instantly. And not just imagery, but also radar information. The signature you can see here in radar, but also in optical, and that merger gives some ability to hone in on the exact pattern, but it's really the challenge of searching all of the data that uncovered and was able to provide our partner with this information. We can also see here the two sites side by side through time and prove that likely the Chinese were building these two installations concurrently. That adds confidence that it is in fact a man-made and military installation. And the reason that we can do this again is because we're ingesting and storing all of this data. So we can go to any location, backcast what the time series of that data looks like, and very quickly add a different lens to the analysis. A few weeks later, the site was reported publicly and confirmed, and what's I think most important is now this signature is going into the database of consistent searches. So as an alert, sitting back as we ingest all of this data, if there's ever going to be another one of these in a visually similar pattern, our customer will know about it. Okay, let's turn to some commercial examples. So, as we mentioned, we look at different commodity supply chains, and here the monetization of predictive analytics takes a different form from the National Defense Challenge, but has equal value or value capture in different ways. In agriculture, the key variable to predict is how much crop is going to be produced during a growing season. And so what you're seeing here on the right panel is a photosynthetic representation on a temporal composite. You can see the seasons pulse in and out. That's a 15-year composite. And at each location, we're drawing the biomass curve up on the upper right, and that is training data for our model. So when we come to today's moment, if it's early in the growing season, we can see how the pattern is emerging, compare it to all of the others, and make a statistical projection of what the total output is going to be. That output, if it's got a tight error bar, is a very valuable tool for partners who physically and commercially trade grain. Our partner here was originally Cargill, the largest grain trader in the world, and they use this for their corn, soy, wheat, and other markets. Again, both physically and financially transacting. We can do the same thing for shipping. Here we have the location of every vessel in a superset of the AIS data. If we combine that with things like upstream port inventory and downstream demand factors from crops or from metals, we can build a statistical model that looks at what the change in shipping prices is going to be by route, by vessel class. These things that we're observing are deterministic fundamental factors, and we know because we have that ability to backcast that they have a predictive and causal relationship with what we care about, in this case, price. So if you're in the logistics industry and looking to book freight, or if you own vessels and want to optimize your fleet, this becomes a very powerful tool for you. In sustainability, we're looking at, for instance, deforestation. Here we're using radar, so it's cloud penetrating because we want to be as contemporary as possible in our data capture to report. And we look at, through time, the accumulation of this activity and predict where there might be deforestation next, here in the red outline. Our partner here is Unilever, and what you're seeing is the palm oil supply chain in Malaysia and Indonesia. They use this system to certify that their products are sustainably sourced, but they also give back to the local government to try and prevent further forest loss. And finally, when we think about sustainability, we can think about also renewable energy. This example, we merged several data sets together, the first one being the global location of every solar panel, photovoltaic, together with a global weather data set that comes from NOAA. And here we extract the solar irradiance value. We also know the cloud fraction at each of the location. So you can imagine the join of those three things simulates sunlight hitting solar panel. And when sunlight hits solar panel, you can build a machine learning model that predicts electricity generation. And what you're seeing here on the right on those curves is our model compared with the California state regulator's actual numbers. And you can see the fit is very high. And the efficacy of this model, therefore, gives us confidence to be able to point it anywhere else and say, this is where you should site your solar panel. This is how you should operate it. This is how you might trade electricity from renewables. So what's common from all of these examples is a few things. First of all, it's massively intensive in terms of compute. We are dealing with huge amounts of data because we're ingesting all of it and throwing most of it away, looking for those indeterminate value or patterns. But the job requires a lot of compute. The second is we need as many data sets as we can find. We want to add to the richness of that digital twin of the planet. And then we have to do it so that we don't break the bank. We have to be on the cost performance curves that make it an economic value for our partners. So as Clint mentioned, the first challenge is that this is not a static industry. This is an exponential industry. I read a statistic that a couple years ago there was approximately 3 million square kilometers per day of total imagery collected of the Earth, and that's going up by an order of magnitude in the next few years. The consequence of that, if you do the math on the data rates, puts the challenge, if your mission is to analyze the data as it's ingested at the rate of collection, beyond the capability of most purpose-built systems. Is really only the commercial cloud with its virtualized compute capacity that can handle the burst that's required to be able to look at every pixel as it comes down. And so as Clint mentioned, we're quite proud of our legacy from Los Alamos in terms of high-performance compute. And in talking with the AWS team, we wondered how we could sort of demonstrate this to the world. And the suggestion was, let's participate in the annual supercomputing competition. It's called the Top 500. As Clint said, we came in number 40. I think if you take out all the other systems that are on-prem and purpose-built, we're probably within the top few cloud supercomputers in the world. One of the AWS team, by the way, told me that the 41st supercomputer cost $100 million and took almost a year to build. So I think we did ours over Memorial Day weekend, and I don't know what they charged us, but it's a good result. So the second challenge is then to have all of this source information. We need the raw repository, the L0, the raw image or radar or whatever sensor data in one place. And the reason for that is because it's extremely expensive to copy and egress data sets if they live somewhere else, and it's optimal to analyze them where they live sort of natively. So if we look at all the most common data sets that we're leveraging for the patterns that we're creating, they come from NASA, from ESA, from NOAA, from the commercial satellite vendors. And the vast majority of those have chosen AWS as their raw repository for information. I think that alone makes it worth locating our system here because we're on top of the data we need. But I think additionally, we see the investment that Clint's team is making in attracting future data sets. The next constellation that we don't even know about is a very powerful idea that will maintain our leadership in terms of being able to see these data sets. If I was launching a constellation, I would choose AWS from a ground station capability all the way up through the services they offer to the marketplace. And so the punchline for us is that we've recently moved the majority of our workloads over to AWS. It was for those reasons I just went through, but a few additional ones as well. Given our requirements from our government customers, the ability to work in classified workloads, have the authority to operate, all the consequent security and permissions, really AWS is the choice for us. The technology leadership, we talked about the supercomputing and their investment in the space, and so we're really thrilled to be able to partner the way that we have with AWS. Finally, we've put a little demo online. So this is a live object search demo. It's called search.descarteslabs.com. If you go to it, you can click on anything you see and instantly find the top 1,000 matches. The data's old and it's just object-oriented, but if you have a bigger problem that fits the kind that we've talked about here today, please get in touch with us. So I'd like to thank again Clint and the AWS team, and I guess we're going to take questions if there are any from the audience.
Yeah, thank you. How about a round of applause? That was a great presentation. Thank you very much, Adam, and if I could have my mic on just a second. So in the 3.5 minutes we have left, Adam has agreed to take a few questions. So if we have any questions from the audience, that would really be valuable. And you can queue up to the microphones if you have a question. While we're waiting for that, I would like to tease out, so that missile example that you used as a national security practitioner, of course, I'm really interested in that. How long did it take you to train that data to be able to identify that site that, according to unclassified reporting, had not yet been discovered? Really curious about that.
Yeah, the answer is was less than 30 minutes to discover the second site. But that belies the fact that there were thousands of hours to prepare for that moment. We had to ingest and prepare all that data, make it analysis ready, have the tooling to be able to train the classifier and then go search against that data. So because that pre-work had been done, it was really just kind of the touch of a button. Interestingly, I think we did that on a laptop from a hotel in Hawaii. So
extraordinary. So that really shows the power of AI and ML, and especially when you can build tailored applications to go after a specific problem set. So that's really powerful. Other questions, please? We've got 2 minutes left.
Hi, Adam. Thank you. Great presentation. Looking back at your HPC experience, and you talked about the necessity of the sensor data, and government has a tendency to silo their data. How are you advising them to get it closer to HPC?
Well, yeah, and that is a persistent challenge. The first step for us is to go where the government wants us to go. I think there was a quote from the CIA the other day that said, on its worst day, AWS was more secure than the client servers that they were working. So that doesn't solve the whole problem, but it moves us towards a moment where we can have real integration of the raw data. There are techniques we can use to look at metadata and cross-correlate that. But ultimately, the system of having a single pipe that comes down into one location where you're analyzing, searching for those patterns as that flood comes through is the goal. Because of permissions and security, we're not quite there. We've looked at replicating our cloud system on-prem in more classified environments, and that is a direction that we'll go if it's a requirement. But unfortunately, there isn't one single place that all of this data is going to live, and that's probably going to be the permanent future. So we're going to have a distributed analytics capability to deal with the fact that they're not all co-located, but we do obviously prefer and benefit if they are stacked up next to each other.
Other questions? We've got 30 seconds left, so that might be just fine. Okay, well, thank you again. Adam, terrific presentation. Thank you to the Descartes Labs team. Really appreciate you being here.